IEEE Standard C37.23-2017 provides standards for bus supporting structures for electrical power systems. ANSI/IEEE Standard C37.24-2017 offers guidance for evaluation, modification, and requalification of power circuit breakers and associated substation equipment. Section 408 of the National Electrical Code, NEC, also covers bus bar requirements. The formula for calculating bus bar bracing is B equals I squared times L squared divided by the quantity 8 times T times D. In this formula, B represents the bracing force in pounds, I is the maximum short-circuit current in kiloamps, L is the effective length of the bus bar in feet, T is the allowable tensile stress of the bracing material in pounds per square inch, and D is the diameter of the bracing material in inches. The procedure for calculating bus bar bracing involves several steps. Firstly, determine the maximum short-circuit current, denoted as I, from the power system study. Secondly, measure the effective length, denoted as L, of the bus bar. Thirdly, choose an appropriate bracing material and determine its allowable tensile stress, denoted as T. Fourthly, select a bracing diameter, denoted as D, that will withstand the calculated bracing force, denoted as B. There are additional considerations to keep in mind. Firstly, the formula assumes that the bracing is uniformly distributed along the bus bar. Secondly, the bracing must be designed to resist both lateral and vertical forces. Thirdly, anchorage points for the bracing should be located to minimize bending stresses in the bus bar. Fourthly, the bracing system should be designed to allow for thermal expansion and contraction of the bus bar. As an example calculation, consider the following values. The maximum short-circuit current is 10 kiloamps. The effective length of the bus bar is 10 feet. The allowable tensile stress of the bracing material is 60,000 pounds per square inch. The desired bracing diameter is 1.0 inch. Substituting these values into the formula, we get B equals 10 squared times 10 squared divided by the quantity 8 times 60,000 times 1.0, which equals 8,333 pounds. Therefore, a bracing diameter of 1.0 inch is sufficient to withstand the bracing force. When determining the maximum short-circuit current from the power system study, it is crucial to consider the worst-case scenario. This involves analyzing various fault locations and system configurations to identify the highest possible fault current that the bus bar might experience. This value is essential for accurately calculating the bracing force. Measuring the effective length of the bus bar, denoted as L, requires careful consideration of the bus bar's geometry and support structure. The effective length represents the distance between bracing points and influences the bending moment and stress experienced by the bus bar during a short-circuit event. Accurate measurement is crucial for proper bracing design. When selecting an appropriate bracing material, factors such as yield strength, tensile strength, corrosion resistance, and thermal expansion coefficient should be considered. The allowable tensile stress, denoted as T, is a critical parameter that dictates the maximum stress the bracing material can withstand without permanent deformation or failure. It is essential to consult material specifications and industry standards to determine appropriate values for allowable tensile stress. Selecting a bracing diameter, denoted as D, involves balancing the desired strength and stiffness with practical considerations such as cost, availability, and ease of installation. A larger diameter bracing provides greater resistance to bending and deformation, but may also increase the overall weight and cost of the bracing system. The calculated bracing force, denoted as P, represents the total force that the bracing system must withstand during a short-circuit event. This force is distributed among the individual bracing elements, and the design must ensure that each element can safely carry its share of the load. Finite element analysis and other advanced modeling techniques can be used to verify the adequacy of the bracing design. The formula B equals I squared times L squared divided by the quantity 8 times T times D provides a simplified representation of the forces acting on a bus bar during a short-circuit event. While this formula is useful for preliminary design calculations, it is important to recognize its limitations. The formula assumes that the bracing is uniformly distributed along the bus bar, which may not always be the case in practice. Additionally, the formula does not account for factors such as the stiffness of the bus bar, the flexibility of the supports, and the effects of dynamic loading. For more complex bus bar systems, it may be necessary to use more sophisticated analysis techniques to accurately determine the bracing requirements. Bracing must be designed to resist both lateral and vertical forces that can arise during a short-circuit event. Lateral forces are typically caused by the magnetic forces generated by the fault current, while vertical forces can be caused by the weight of the bus bar and any attached equipment. The bracing system must be capable of withstanding both types of forces without excessive deformation or failure. Anchorage points for the bracing should be located to minimize bending stresses in the bus bar. Bending stresses can concentrate at locations where the bus bar is rigidly supported, and these stresses can significantly reduce the bus bar's ability to withstand short-circuit forces. By carefully selecting the location of the anchorage points, it is possible to distribute the stresses more evenly and improve the overall performance of the bus bar system. The bracing system should be designed to allow for thermal expansion and contraction of the bus bar. Bus bars can experience significant temperature changes during operation, and these temperature changes can cause the bus bar to expand and contract. If the bracing system is too rigid, it can restrain the bus bar's movement and induce stresses that can lead to fatigue failure. The bracing system should incorporate flexible elements or expansion joints to accommodate thermal movement without inducing excessive stresses. In addition to the bracing force, the bus bar and its supports must also be able to withstand the effects of electromagnetic forces, mechanical vibrations, and environmental factors such as corrosion and moisture. These factors can significantly impact the long-term reliability and performance of the bus bar system. Regular inspection and maintenance are essential to identify and address any potential problems before they lead to failure. The selection of appropriate materials for the bus bar and its supports is crucial for ensuring the long-term reliability and performance of the system. Copper and aluminum are commonly used for bus bars due to their high conductivity and corrosion resistance. The supports can be made of steel, aluminum, or composite materials depending on the specific application requirements. The materials should be selected to withstand the expected environmental conditions and to minimize the risk of galvanic corrosion. The design and installation of bus bar bracing systems should be performed by qualified engineers and technicians with expertise in electrical power systems and structural engineering. The installation should be carefully inspected to ensure that all components are properly installed and that the bracing system meets the specified performance requirements. Regular maintenance and inspection should be performed to identify and address any potential problems before they lead to failure. The formula for calculating bus bar bracing provides a valuable tool for designing safe and reliable electrical power systems. By understanding the factors that influence bracing force and by carefully selecting appropriate materials and construction techniques, it is possible to create bus bar systems that can withstand the rigors of short-circuit events and provide long-term reliable performance. Remember to always consult with qualified professionals and adhere to relevant codes and standards when designing and installing bus bar systems. Short-circuit current is typically provided in symmetrical root mean square kiloamps. The available fault current at the switchgear location must be acquired. Sometimes utility companies will provide it to you, or it could be found from an arc flash study. The effective length of the bus bar should be the length between the center of the supports. The calculation for bus bar bracing also depends on the shape of the bus bars. The example formula given is for rectangular bus bars. For other shapes, such as square or circular, the formula will need to be modified. It is important to consider the mechanical properties of the bus bar material when calculating the bracing requirements. The yield strength, tensile strength, and modulus of elasticity of the material will all affect the amount of stress that the bus bar can withstand. The bracing system must be designed to prevent the bus bar from exceeding its allowable stress limits. The bracing system should also be designed to prevent the bus bar from vibrating excessively during normal operation. Excessive vibration can lead to fatigue failure of the bus bar or its supports. Vibration dampers can be used to reduce the amplitude of vibrations. The bracing system should be designed to be easily accessible for inspection and maintenance. Regular inspections should be performed to check for signs of corrosion, damage, or loose connections. Any problems should be addressed promptly to prevent failure of the busbar system. The busbar bracing calculation is an important part of switchgear design. By carefully considering all of the relevant factors, it is possible to design a busbar system that is safe, reliable, and long-lasting. The information provided serves as a general guide and should not be considered a substitute for professional engineering advice. Always consult with a qualified engineer to ensure that your busbar system meets all applicable codes and standards. Firstly, verify the accuracy of the power system study. Secondly, confirm the material properties of the busbar and bracing. Thirdly, validate the bracing design with finite element analysis. Fourthly, inspect the installation for proper alignment and tightness. Fifthly, implement a regular maintenance program. The formula B equals I squared times L squared divided by the quantity 8 times T times D is a simplified equation for calculating the bracing force on a busbar. This equation assumes that the busbar is a straight, rigid conductor with uniformly distributed bracing. In reality, busbar systems can be more complex, with varying geometries, non-uniform bracing, and flexible supports. Therefore, it is important to understand the limitations of this formula and to use more sophisticated analysis techniques when necessary. Firstly, the formula does not account for the effects of electromagnetic forces. When a short circuit occurs, the high currents flowing through the busbar can generate strong electromagnetic forces that can cause the busbar to move and deform. These forces can be significant, especially in high current systems, and they must be considered in the bracing design. Secondly, the formula does not account for the effects of mechanical vibrations. Busbars can be subjected to mechanical vibrations from various sources, such as rotating equipment, seismic activity, and wind loading. These vibrations can cause fatigue failure of the busbar or its supports if they are not properly addressed. Thirdly, the formula does not account for the effects of thermal expansion and contraction. Busbars can experience significant temperature changes during operation, which can cause them to expand and contract. This expansion and contraction can induce stresses in the busbar and its supports if they are not properly accommodated. The bracing system should be designed to allow for thermal movement without inducing excessive stresses. Fourthly, the formula does not account for the effects of corrosion. Busbars can be exposed to corrosive environments, which can weaken the material and reduce its ability to withstand short-circuit forces. The bracing system should be designed to protect the busbar from corrosion. The formula assumes that the bracing is uniformly distributed along the busbar. However, this may not always be the case in practice. In some cases, the bracing may be concentrated at a certain point along the busbar. The effect of concentrated bracing is that the bracing force at those points will be higher than the average bracing force calculated by the formula. The bracing system must be designed to withstand the maximum bracing force at any point along the busbar. The formula assumes that the bracing material is perfectly rigid. However, in reality, the bracing material will have some degree of flexibility. The flexibility of the bracing material will reduce the amount of bracing force that it can withstand. The bracing system must be designed to account for the flexibility of the bracing material. The allowable tensile stress, denoted as T, of the bracing material is a critical parameter that dictates the maximum stress the bracing material can withstand without permanent deformation or failure. It is essential to consult material specifications and industry standards to determine appropriate values for allowable tensile stress. Factors such as the type of material, the temperature, and the loading conditions must be considered when selecting the allowable tensile stress. The bracing diameter, denoted as D, is another important parameter that affects the bracing force. A larger bracing diameter will provide greater resistance to bending and deformation. The bracing diameter should be selected based on the calculated bracing force and the allowable stress of the bracing material. The example calculation provided shows that a bracing diameter of 1.0 inch is sufficient to withstand the bracing force of 8,333 pounds. However, this is just an example, and the actual bracing diameter required will vary depending on the specific application. The design of busbar bracing systems is a complex process that requires careful consideration of all relevant factors. The formula for calculating busbar bracing provides a valuable tool for designing safe and reliable electrical power systems.